In this video, we're going to talk about electrophilic additions to conjugated dienes. And we're going to see some parallel to the electrophilic addition to just alkenes that have been covered previously. But here we're looking at the addition to the dienes. And in the video that talks about conjugated systems, we mentioned having kind of two spots where the diene will act as an electrophile. And that is going to be very important with this reaction. So alkene addition reaction refresher. So we want to remember a few key points from this reaction. So let's just look at an example. So if I have an alkene, I can react with a number of things. One reagent that's common is some kind of acid halide. So HCl is a good example. We need a aprotic solvent. So ether is a great solvent for these addition reactions. And what's going to happen is the electrons from the double bond are going to form a new bond with the hydrogen, and the electrons in that HCl bond are going to become a lone pair on the chlorine. So if we notice, we've got two carbons that were involved with those pi electrons, one kind of on the left, one on the right, and they are substituted differently. So the one on the left has one carbon attached to it, and the one on the right has two. So we need to decide which is the carbon the hydrogen is going to actually add to. And if you recall, we had something called Markovnikov's rule. And this rule told us that the hydrogen is going to add to the carbon that already has the most hydrogens. So if we look at our starting structure, the carbon on the left would have one hydrogen, because it's showing three bonds, so the fourth missing is a hydrogen. The carbon on the right already shows four bonds, so there's no hydrogens. So that means in the intermediate here, the hydrogen is going to add to that left carbon. So there was already one hydrogen, and I'm going to add in the second one. Make it white to be consistent here. Okay. That then leaves a positive charge on the other carbon of what was the double bond. So we have our carbocation. So this is our carbocation intermediate. And we've also formed a chlorine ion, chloride ion really. That ion is going to now attack the carbocation, and we form our final structure. So in the end, what's really happening here, and the reason we have the Markovnikov's rule, is for carbocations, tertiary are more stable than secondary, more stable than primary, so much that primary is not going to happen. Secondary, maybe. Tertiary is always going to be the preferred if possible. And we even get shifts if we need to get to a tertiary carbocation, hydride or methyl shifts. So again, all of this is review. If any of this doesn't sound familiar, it might be worth going back and reviewing the addition reactions of alkenes, because we are going to expand on that here. So for electrophilic additions to dienes, the big key here is that you are going to get mixtures. And what you need to do is decide, based on conditions, which products are going to dominate, what the mixture will actually look like, and why. So let's just kind of jump in and look at an example. So I'm going to start off with just a simple diene. Again, HX, in this case I'm going to look at HBr specifically, is a very common reagent. And I'm going to go ahead and tell you that we're going to get two potential products here. So I could get the bromine to add in this location, or it could look something like this. Now notice with that second product that the double bond has moved. Okay, so to get a double bond to move, we're going to have likely some kind of resonance going on. So what we actually have here, and just some terminology, this first product is called a 1,2 product, and the second is called a 1,4. And the reason for that is we're not just adding the bromine, we're also adding the hydrogen. So in this first structure, the hydrogen would have added here to the end. And the second structure, that hydrogen also added to the end. So notice we've got 1, 2 for the 1,2 product versus 1, 2, 3, 4 for the 1,4 product. So this is not connected to naming for the numbering, it's just how the two pieces that we're adding are related to each other. I will tell you what we do not get as a product is we will not get the bromine to add on the end and keep the double bond also on the end. So that product does not form. So let's try to think about why. So if we're going to do the addition, we know that we add hydrogen first. And in this case, our two double bonds are equivalent. So we don't need to think about which one is going to react. We're just going to focus in on one because they are the same. That will be different if we have non-equivalent double bonds, and we'll look at that in the next example. So when we add our H, just like we did with the single alkene in the previous example, the hydrogen is going to add to the carbon with the most hydrogens. So my starting structure, the end carbon has 2 hydrogens and the inner carbon has 1. So here's those original hydrogens. So that means the hydrogen that I'm adding is going to add to the end, which will put the carbocation on the second carbon. This is a secondary carbocation. Had I done the opposite, the carbocation would have been on the end and it would have been primary, and it's not stable enough to form. So now that the carbocation there is on the inside, that is where the bromine will add. So I'm going to not write in the hydrogens just for clarity. So here is how we got to that 1,2 product, right? Pretty much just like we did with the addition reactions to double bonds. The difference here is now we're getting this second 1,4 product that we need to think about. So what's going to happen is we have this carbocation, and this is slightly different than just a regular carbocation. This is called an allylic carbocation because we have the carbocation 1 carbon away from a double bond. And what this does is it creates an opportunity for resonance. So I can kick those electrons in. That then moves my positive charge out to the end. And now you can see why we get the 1,4 product, because now the bromide ion will come in and add on to the ends. And we also see that the double bond has shifted to the middle. So we've shown how we get to the 1,2 product just through the carbocation that's formed directly, and then how we get to the other 1,4 product through an extra resonance structure step of the carbocation. So let's look at an example where we do not have equivalent double bonds. All right, so we're going to have a structure. And this example, the structure is a little more complicated, but you really want to just focus in on the diene portion of it. The rest you can kind of ignore. Not entirely, but kind of. So we've got 2 different double bonds here. So let's think about all the different places that we could form the carbocation, meaning all the different places we can add hydrogen as our first step. So if I look at this double bond on the right, I have 2 options. I could add the hydrogen to this carbon that's on the left side of the double bond or the one that's on the right. So if I think about Markovnikov's rule, I'm going to add the hydrogen to the carbon that has the most, and that's going to be the one on the right because it has 1 hydrogen. So if I add the hydrogen to the right carbon, there's already 1 hydrogen there. I'm going to add the second. That means the carbocation is up here on the left carbon, and I have not touched the second double bond. So that's one option. If I go back to my starting material and now focus on the other double bond, the 2 places that I could add hydrogen are kind of up here at the top or down here at the bottom. The top carbon does not have any hydrogens. The bottom has 1. So I'm going to add my hydrogen to the bottom carbon. So again, I'm not touching the double bond that's outside the ring for now. I had 1 hydrogen down here. I'm now adding a second, and that leaves my carbocation up on that top carbon. So here are the 2 options. And notice in both cases, you are forming a tertiary carbocation. So there's really no selectivity here. Both of these could be formed as your initial carbocation. So if that's the case, let's think about what the products are going to be. Again, you're likely going to get 1, 2, 1, 4 options. So the 1, 2 is where we just add the bromine straight to where that current carbocation is. So we'll add the bromine there. I can also draw my resonance structure. So I'm going to shift that double bond out to where the positive charge is. So there's the double bond, which is going to leave the positive charge down here. And now that is where I can add the bromine to form the 1,4 product. So notice when you're doing this, and you can go back and look at the previous example and see it there as well, one of the double bonds is going to end up shifting to in between where the original 2 double bonds were to get to the 1,4. And then the bromine will add kind of to the far end. You'll have to decide which end, okay, of where the conjugated system was to start. So you can kind of start to get a feel. It's always good to draw out the carbocations and see how they move around with resonance, but you'll start to get a feel for what the 1, 2 and 1, 4 products look like. So again, 1, 2, I can just add the bromine to the initial carbocation location. So there's the 1, 2 product. I can draw a resonance structure. So I'm going to kick the double bond into where the positive charge is, which then leaves the positive charge out here on the right side. So that is where the bromine can add for the other possible 1, 4 products. So something I didn't say here originally, we are reacting this with HBr, just to clarify there. The other thing, and I should have said this on the previous slide, we're really working with just one equivalent, because if we had 2, there's nothing stopping the HBr from reacting with the second double bonds. But if we can hold ourselves to one equivalent, we can hold ourselves to just a single addition. And for the sake of this section of content, we're going to focus on just the single addition. So because both of our initial carbocations were tertiary, so this carbocation and this one, like I said, there's nothing distinguishing one from the other as far as better or more likely to form. They're both going to form. If we compare the 1, 2, 1, 4 products to each other, and we're going to talk about this in a later video, we do have a preference for either 1, 2 or 1, 4, depending on the conditions. But for now, we don't have a preference based on our understanding of carbocation stability from that first step.